Hello everyone, this is Dr. Shine. Today I am going to discuss about Thevenin's theorem. On a previous session, we have discussed how we can calculate the equivalent resistance of a complicated series parallel connection of resistors and how current flows through from higher mountain to lower mountain peaks, or how the current flows through different resistors when they are in series parallel connection, when it is called series parallel connection. So this discussion of previous session will be implicated in this session in the further slides. So why basically we need to apply this Thevenin's theorem? Why we need to apply this Thevenin's theorem? Let's take a look. Here in this circuit, we know the voltage sources, the voltage amount, we know the resistance, but we have no idea about the branch current. So if someone is asked to calculate the branch current of AB, we have no idea how we can calculate this. So here the Thevenin's theorem comes into the picture, where we need to calculate the Thevenin's equivalent resistance, Thevenin's equivalent voltage to extract the amount of current flows through this AB branch. Thevenin's theorem basically states that it is possible to simplify any linear circuit irrespective of how complex it is to an equivalent circuit with a single voltage source and series resistance. So the equivalent circuit of this complicated connection of series parallel connection is like this. So the Thevenin's equivalent circuit look like this, where there is Thevenin's equivalent voltage present, Thevenin's equivalent resistance present, that is RTH, VTH, and one series resistance, that is R2 or RL. This resistance is basically the resistance across AB. Or we can term this branch as load branch, load current. Since this resistance or this branch gives us the load of calculation, so we can remember like this also. So this branch is also called load current. So when someone is given us load, we always try to vanish this, omit this from the circuit. So let's vanish this branch AB. Okay, now it's fine. So when we are going to calculate the Thevenin's equivalent resistance, there is no need of the voltage sources. So we may take the short circuit here also. So finally the circuit looks like this, and we can see that the two resistors R1 and R3 are in parallel connection across the branch AB, or across the point AB. So we have removed the branch, so we can term this like AB point here. So across the AB point, the two present resistors R1 and R3 are in parallel connection. So we know how to calculate the equivalent of two parallel resistance, that is R1 into R3 divided by R1 plus R3. Now we need to calculate the Thevenin's equivalent voltage. So again we will remove this AB branch. This is give us too much load of calculation. We will remove this. Now here we cannot short circuit this voltage sources, because we need to calculate the Thevenin's equivalent voltage here. So we cannot remove this voltage sources, or we cannot remove the resistance also. You may say that here now we are calculating VT, so why the need of this resistance? But the thing is that there is some voltage drop in the resistance, not some voltage drop. A huge amount of voltage will drop across the resistance. Or we may compare this in the river flow pattern also. When river flows through the path, some soil soak the water. So same here also, when current flows through the resistors, some current will drop here. So the drop is recognized as voltage drop, not the current drop. So when current flows through the resistors, voltage drop will happen here. So here we can see that there are two voltage sources, B2 and B1, and same as the phenomena of river flow, here also current will flow from the higher point towards the lower point. So here higher point is higher peak mountain point is B2, so it will flows from B2 towards B1. So let's start the calculation part here. V2 voltage, that is 20 voltage, minus why? Because voltage drops across R3 resistor. So 20 minus 20 into I, that is R3 into I. Again voltage drop across R1 resistor, that is R1 into I, that is 10 into I. And here we can see that the current flows from the positive or peak point of the mountain towards the sea level. That's also here minus, plus to minus it is flowing. Therefore here also it is minus 10. So from here we can calculate the current I, that is 10 by 30 or 1 by 3 ampere. Now we can calculate the Thevenin's equivalent voltage, that is VTH. VTH is nothing but the voltage across the point A and B, that is VAB. So again let's calculate from B2. B2 voltage, that is 20, minus voltage drop across R3 resistors, that is 20 into I. We know the value of I here. So from here we can calculate the VTH also, that is 40 by 3. Now let's see the Thevenin's equivalent circuit. So here we know the value of VTH, we know the value of RTH also, and the load branch resistance is already given, that is 40 ohm. So here we can see that the resistor RTH and RL are in series connection, agree or not? These two resistors are in series connection because there is no splitting up of path, no division of current flow, only a path change, but there is no obstacle in between them, therefore no splitting up of path. That's why this RTH and RL are in series connection, and we know the equivalent of two series resistance, that is simply we can take the summation of these two. So here the load current RL is equal to VTH divided by RTH plus RL, that is 1 by 3 ampere. Thank you.